You know, the next time you're driving, just cruising down the highway, I want you to try something. Take a second and really look at the road itself. The lines, the way a curve just flows, the slope, it all just feels normal, right? Like it's always been that way. But what if I told you that every single one of those details is the result of some seriously complex science, all designed to keep you safe and comfortable, even at crazy speeds? Well, today, we're going to pull back the curtain on that hidden science.
I mean, really think about it. Why isn't a highway lane, say, 2 meters wide or 5? Why does one curve feel totally fine at 100 kilometers per hour, but another one would be absolutely terrifying? I promise you, none of this is accidental. It is all meticulously, and I mean meticulously, planned.
And the answer to all those questions? It's in this document, the Korean Design Standard, or KDS. The best way to think about it is like a master blueprint or a giant recipe book for every single public road in the country. It's this huge collection of physics, human psychology, and pure engineering. And we're going to use it to, well, build a road, piece by piece.
Okay, so to get how a road really works, we need to start by looking at a cross-section of it. Imagine we just sliced right through the pavement. Engineers in Korea call this the Hwangdong Gusong. So let's build out this slice, starting with the most basic, fundamental piece of the puzzle. The lane, or taro. It's the space your car lives in, right? The KDS says it's where a single line of cars can travel, marked out by lines. Simple enough. But its most important feature isn't the paint on the ground, it's the width. And that width? It's not just a random number someone picked. The KDS is super clear about this. The faster a road is designed for, the wider the lane has to be. So, for a highway built for speeds over 100 kilometers per hour, you need at least 3.5 meters. Drop down to a local road at 60 and it can shrink to 3 meters. Why? Well, that extra space at high speeds gives you more room for error and just makes you feel less crowded, which is a massive factor in keeping drivers comfortable and safe.
All right, so we've got our lanes. What's next on our road slice? We add the shoulder, or gatgil. Now, it's really easy to just think of this as a spot for breakdowns, right? But its job is way more important than you'd think.
The KDS actually spells out 4 key functions for the shoulder. Yeah, okay, number 1, it's a safety valve for emergencies. We all know that. But it also provides critical structural support to the main lanes, stopping the edges from literally crumbling away. And then there's the psychological part. It gives you a sense of openness, so you feel less boxed in and more relaxed. And it's also vital for drainage, getting water off the road. It's a real workhorse.
The last piece of our road slice is the median, or Chuman Pulide. On any high-speed, multi-lane road, this is the absolute non-negotiable feature that prevents head-on collisions. And just like everything else, its width and what it's made of, whether it's a concrete barrier or a grassy patch, is also strictly controlled by the KDS, all based on the road speed and where it is. So, we've built our basic slice of road. But a road isn't just a flat, straight line, is it? It has to curve, it has to go up and down hills, it has to navigate the real world. This is where we get into what engineers call the art of alignment. Engineers think about this in 2 main ways. You've got horizontal alignment, which is basically the road's path from a bird's eye view, all the straight parts and the curves. Then you've got vertical alignment. That's the side view, the hills and valleys, what they call grades. Making these 2 work together perfectly is the secret to a smooth, safe drive.
Now check this out, because this is where it gets really interesting. This is just pure physics. The KDS sets a minimum radius for every curve, and it's all based on speed. At 120 kilometers an hour, a curve has to have a radius of at least 710 meters. That's a super, super gentle curve. But down at 40 kilometers an hour, you can have a really tight 60-meter radius curve. The reason? Centrifugal force. If you go too fast on a curve that's too tight, your car just wants to keep going straight, right off the road.
But engineers have this awesome trick up their sleeve to fight that force. It's called super elevation, or pyeongyongsa. This is that banking you feel when you're on a highway on-ramp. By tilting the road into the curve, they actually use your car's own weight to help pull it towards the center of the turn, fighting that outward push. And you guessed it, the KDS has these super precise tables that tell them exactly how much to bank the road for any given speed and curve.
Okay, so we've built our road slice, and we've curved it through the landscape. But none of that matters one bit if the driver can't see what's coming up. And that brings us to what is, arguably, the most critical safety element in all of road design, the science of sight.
This whole concept is called stopping sight distance, or 정지시고. And this one rule pretty much dictates everything else. Engineers have to ensure that at any point on a road,
a driver can see far enough ahead to spot a hazard, react, and brake to a complete stop. This isn't a guess, it's a very specific calculation.
So the total stopping distance is made up of two parts. First, you've got the reaction distance. The KDS assumes it takes the average driver about 2.5 seconds to see a problem, process it as a danger, and actually get their foot on the brake. For those 2.5 seconds, your car is still flying along at full speed. The second part is the actual braking distance, how far your car physically skids after you hit the brakes, and they even calculate it for wet roads, just to be on the safe side.
And this chart right here, this is the whole ball game. The relationship between your speed and how far you need to stop isn't a straight line, it's exponential. At 60 kilometers an hour, you need 75 meters, but at 100, you don't just need a little more room, you need more than double that, 155 meters. And this is exactly why you can't have a sharp hill or a blind curve. The road's geometry must give you this minimum sight distance, always. So let's pull all these pieces together. Every single rule we've talked about, how wide a lane is, the radius of a curve, the banking, the sight lines over a hill, they aren't just isolated decisions. They are all interconnected parts of a massive system that's designed around a few core ideas.
The KDS is really built on these four pillars. Safety, obviously, is number one. Efficiency is all about making traffic flow. Comfort is about making the drive feel natural and not stressful. And consistency is huge. A road should never surprise you. You shouldn't be cruising along a gentle highway and suddenly get hit with a sharp, unbanked turn. The design has to meet your expectations as a driver.
But here's the thing. All of this incredible, meticulous science is based on the limitations of a human driver. But what happens when the driver is a computer? As self-driving cars become more common, will we still need 3.5-meter lanes? If reaction time becomes basically zero, how much shorter can our stopping sight distances get? This rulebook that has defined our streets for decades, it might be on the verge of its biggest rewrite ever. Something to think about on your next drive.